everything we talked about until now were all concurrent statements, and we said everything happens all at once. And well, we've done a few things like putting in text, a structural description. We've done a little bit of data flow that we could have probably did ourselves if we really want to in a schematic. I mean, you could do some pretty sophisticated stuff, but this is where Verilog really has its power, and that's the procedural design. So I will leave the example running over there, and I will go through what procedural design actually means. Just to begin with, a procedural design, the way it's different than concurrent design, is that here things will start running in sequence, just like you expect a C program to do. So one line after the other in a sequence. It's not so obvious how these things are actually being implemented in hardware. And in a way, if you are a Verilog designer, you don't really care about how the synthesizer then go and implement it. Of course, there are ways to write your code in such a way that will get the synthesizer to implement a better design for you. But as long as you follow the structure, the synthesizer will be able to pretty much implement anything that you want. Now, we'll start off with defining blocks, and we will talk about an always block. So first of all, an always block is going to be a list of statements enclosed in this block that will run in sequence, one after the other. Now, the instructions that we will cover, and this is from now until the end of the lectures, are all going to be procedural statements, procedural instructions that are not the same as everything we covered up until now. Anything, things like assign and, well, assign is the main keyword that we've seen, and the structural description that we've done before should stay in the sort of bulk of your module, things that will run in parallel. Anything that you want to put inside a procedural block will have special keywords between them. One of the important things is to realize what instructions are procedural instructions, what instructions are concurrent instructions, and hopefully this distinction will sort of become evident when you understand what they do. So the idea behind an always block is that it's going to be a block of code that's going to be sitting there idle, not doing anything. It will just sit there until something will come and trigger it, and then it will execute one line after the other, similar to a program. Now, that thing that can actually trigger it is what we call signals in the sensitivity list. The sensitivity list is anything that is going to be inside the brackets here. And the way we sort of say it, it's always at some signal, always at x. Whenever there's any change in x, whether x will change from 0 to 1, 1 to 0, if x was a vector, if any of the bits in the vector change, anything that happens with x will then trigger this block, and whatever will be in this block will start running. You can do some pretty sophisticated triggering and add pause edge and neg edge modifiers to them, and then you can say things like always at pause edge of clock, which means always at the positive edge of the clock, which translate to trigger this block only when the clock changes from 0 to 1. Don't trigger it on the way back from 1 to 0. And you can sort of already imagine how these will lend themselves nicely to flip-flops. In fact, this is what's going on in the example there, and we will talk about the example. Similarly, you can use the word neg edge to say only in the falling edge of the signal. So only on a transition from 1 to 0. If you don't write either pause edge or neg edge to any of your signal names, any change in the signal will actually trigger your block. Now, you can have more than one signal triggering a block. You can say always at X or Y or Z. Any change in any of those variables will then trigger your block. Just to be pedantic about notation, you can either use the keyword or you can separate the signal names by commas. This is actually an addition into the latest version of Verilog, which is why I didn't put it here. But if you do see commas, same thing as putting in the or word. Now, the keyword always itself, the instruction always, not anything inside, just always itself, is a concurrent statement. You could have few of these blocks inside your overall module, sitting side by side, and all of these blocks will be, in a way, parallel to each other. Once you trigger something, then inside this block, things will be procedural, as in run one line after the other. Again, when we see a few more examples, I mean, it's all fairly abstract, I do want you to sort of remember these definitions, and we'll see how it comes about. Now, in the syntax here, we see that we use always at something and then followed by a procedural statement. This procedural statement may be either one instruction, a procedural instruction or procedural statement that does something, or it can be a block of instructions that are enclosed within a begin and end keywords. You know, it's similar to those people that when they go in front of a screen, they sort of bend down and run. I mean, seriously, if you don't go, just go. I mean, people can see you. It's not going to happen. Usually, when we start an always keyword, we usually want to run more than one statement or one instruction, and we will almost always enclose within a begin and end block. As you can see in the example there, I do say always at something in the sensitivity list begin, and then it ends at the end. Inside this block, you can put as many procedural statements or procedural instructions as you want. Again, if you want to parallel it to C, begin and end is very similar to the curly brackets that you have in C when you open a block and then you close it later. Here we don't have curly brackets, or not for this meaning. We do have a begin and end block. I will go back to talk more about it in the example. Was this a question?
Yeah.
Yes.
Can you replace the always with like a if pause age of clock?
All right, we will talk about if in a few slides' time. I mean, obviously if is a valid Verilog keyword. If is a procedural statement. Therefore, it cannot live in the sort of space of the module. It must be inside a process or inside a block. And this block is opened by an always. So, because you can't have an if that is continuously evaluating, because this is the meaning of a concurrent statement, something that continuously being evaluated, and therefore it will do something. You can't have this. You can have it inside a process, and we will cover if in a few slides' time. Other questions so far? Slightly confusing, but we'll get there. We do have variables in Verilog. If you're observant, any signal names that we use so far were all wires. The input and the outputs were wires. When we assign things, we assign them to wires. We never had a variable. A variable, if you make, again, the parallels to C, is something that can actually store information in it and then retrieve it from the storage later. Now, there's few types of variables in Verilog. The most common ones are either the reg, short for register. There's also an int variable. I will not talk about the int variable that we consider in reg. There's a couple of others, really weird ones that we don't care about. As far as we're concerned, a variable in Verilog is a reg or a register. It is going to be well, a variable or an identifier that can store information inside it. And this information can either be a 1-bit quantity, or it can be a vector, just like multi-bit wire. Now, if you want, you can think about registers in a way as being flip-flops, but I will reserve it by saying that when you have a reg, it doesn't necessarily mean Verilog will implement a flip-flop for you. Because Verilog might be able to optimize this flip-flop out. It might be able to use other tricks to remember or pretend to remember your value. But if it makes it easier for you to comprehend, you can think about it as a flip-flop, or better yet, just think about it as a variable in C. Just something that stores information. Now, if you remember on Friday, when I was talking about output wires, and I said you can write the output, but you couldn't read back from it if you write something to the output. And back on Friday, I reserved it, and I said, unless you define it as a register. And this is something we will do. And this is there in the example. Again, I will analyze this example into details. But you can see that there's an output queue, and I am defining it as a register as well. So it will have a memory. This queue is now a variable that is connected through a wire to the output. But now that it's a variable, I can actually refer to it and read back from it. So that's about variables. The other important thing, by the way, variables only live in a procedural code. You can't use them as in the concurrent statements. You can't continuously assign something to a register. You can't use the assign keyword and have a register on the left-hand side. It's two sort of different parts of the Verilog. Now this is where it gets really fun. We have two types of assignments that we can use in procedural code. We have blocking assignment and non-blocking assignment. Now, once you get confused, stop me. I will try to define as best I can, and I'll give you some examples. We'll start with blocking assignment. Blocking assignment is what you would expect an assignment to be, just like in C. You assign one value to the other, right-hand side to a left-hand side. Like here, the right-hand side could be an expression, it could be another variable, it can be a wire, it could be a more complex expression. And it will be assigned into a variable, to something that stores that value. After it does this, it will move on to the next line of your process, or the next line in your block, in your procedural code. Again, this can only live inside a procedural code, meaning inside an always block, inside a process. The non-blocking assignment is when Verilog takes the right-hand side expression, evaluates it, remember the result, but doesn't actually assign it to the left-hand side. It just remembers it somewhere aside, and then continues running with your code that may have other instructions, may have other non-blocking assignments. When it gets to the end of your process, then all those values in all your non-blocking assignment that remember the side are all being assigned at the same time at the end. Who's confused? One person. Liars.
Can I ask you a question, please?
Yeah.
For non-blocking, so you're saying that only the commands are executed at the end of the process, not like at the right at the end, like you know what I'm saying?
Well, those non-blockings can exist anywhere inside your process. It can be at the beginning, middle, end, anywhere.
It's only executed at the end of the process. Instead of blocking the cycle, you execute it during the whole thing, right?
Yes and no. Blocking one, no, it's, when you say execution, it's being executed, technically it's being executed where it is, but it's being assigned at the end. And why is this important? Because imagine a case where you evaluate a right-hand side somewhere, and as I said, you remember this value somewhere aside. Later in the code, you do some change that will change that right-hand side. But then you get to the end of the code, and what will be assigned is that value that you remembered to begin with, not the value after the change. Let me show you an example of blocking versus non-blocking assignments, and hopefully this will illustrate the difference. Suppose we have three variables A, B, and C, and suppose they contain the values 3, 5, and 8. For this example, these variables are 4 bits variables that contains 4 bits each, and therefore can hold these values. In the case of the blocking assignment, we'll start with B equals A, therefore B will now be equals to what A is equal to. Sorry. Then C will be equal to B. So B is now 3, C will also be 3, and all of them end up being 3. So one is executed after the other, similar to how you would expect a C program to do it. In the non-blocking case, we have B is assigned A, but not just yet. You will look at the right-hand side and say, all right, I'll remember the value A aside. It doesn't assign it to B just yet. You will then go on and look at B, which hasn't changed. B is 5. You will say, all right, I'll remember that value 5 aside, and I'm going to go on with my code. Once it gets to this end there, then all those remembered values will be flushed into the variables. And then B will be assigned with 3, C will be assigned with 5. At the same time, right at the end, everything will be flushed together. Does this clarify the difference between them? All right. Now, why would we want to use one or the other? First of all, we have a few rules of thumb. You don't have to follow these rules if you know what you're doing. This is just sort of recommendation in the general case, but you don't have to apply these if you want to do something different. In general, we will use blocking assignments when we want to describe a combinational logic, things with no memory in them. We will use non-blocking assignment when we have sequential logic, and I will emphasize this point in a second and tell you why it makes sense. Now, usually, the recommendation is don't mix the two in the same block. Now, it's not illegal to mix them. You could if you wanted to, but this is when things will start getting a little bit confusing, because then you usually lose track of what actually has been assigned yet and what will be assigned at the end. If you can keep track and you know what you're doing, fine, mix them together. Usually, for most normal designs, you wouldn't even need to mix them together. You usually choose one or the other, depending on what you want your block to do, and you use one of them. And something that's really important, and a lot of compilers will actually yell at you if you try to do this, don't assign the same variable in two different always blocks. Because imagine the case where you have two always blocks. Now, in a way, what I said before, both of them live in parallel to each other. Each one of them have some sensitivity list, something that will trigger it. And this triggering can happen at any time in the circuit. In fact, let's assume there's some variable x that triggers both of these blocks that exist in both the sensitivity lists, and therefore will trigger both of these blocks. If there is a change in x, both of these blocks will start executing one line after the other. But you don't know how fast or what's the inside implementation, bless you, of each one of these blocks is. So if you have something, for example, a statement here that say y equals 3 somewhere inside this block, and here you have a statement that says y equals 5, after, bless you, after x changes its value, what will be the value of y? Well, it depends which one of these blocks got to assign y first and which one's the later one. But you can't be sure because you don't know how fast those things run. You don't know how they're being implemented, and therefore you should never do it. You should never rely on the fact that this block up there have so many more lines, and that y assignment is towards the end, where this one have only one line. Therefore, you will run quicker. Don't make those assumptions. And in fact, the compiler will usually warn you, if not completely refuse to compile your code. Xilinx, for example, we completely refuse to compile it, and as far as I know, there's no way to override it. You will just say, no, you're trying. Yeah, people are agreeing. So, see, I'm not lying to you.
Let's say you had the same always block, and then you had B non-blocking A, and then B non-blocking C.
Meaning you're trying to assign the same variable
Yes.
with two different non-blocking
so
ones?
B equals A, and then you have B equals C.
The later one will
Okay.
prevail. Yeah.
How does the compiler discern between non-blocking assignment and less than or equal to, which is just context-based?
I'm laughing because this question comes every year. Yes, it's context-based. Unlike C, where you can actually have, say, an equal as an expression, the assignment in Verilog is not an operator. It's a statement. In fact, it's called, if you look at the slide, assignment statement. Therefore, there could never be a mix-up between them. There's no situation where it could be interpreted as either one. Moving on, let me show you some, well, a couple actually, of procedural statements that we can use. We'll talk about the if statement and after that the case statement. Both of them are procedural instructions. You cannot use them outside an always block or outside a process. Now I will reserve what I just said about a process always being an always block. There are other keywords that will open a process, such as initial and forever. You might see them in your simulations in the lab. For now, let's assume that an always keyword is the thing that will open a process for us. However, the if and the case statements, both of them can be used in any process, even if it's opened using a different keyword than just always. So you don't blame me that I was lying to you later. The if statement, again, I'll do the parallels with C, behaves just like you would expect from C. You have some condition in there that will evaluate to either a true or a false. If it's true, then the rest will be executed. Now, this can be either one instruction, or again, it can be a block of instructions starting with a begin and end. You can also have if-else, so you can have an else statement to it to say, if this is true, execute this instruction or instructions, or block of instructions. Otherwise, if this was not true, then execute this instruction or block of instructions. Very similar to how you do it in C, only replace your curly brackets with the begin and end keywords. I think we now know enough to go back to our example there and analyze what's going on. I'm pretty sure a lot of you sort of figure out by now what it does, but there are quite a few things that I want to draw your attention to. So obviously this is a flip-flop because it says it's a positive edge trigger D flip-flop. That will have a reset signal. And obviously we'll have an output Q. In this particular implementation, we don't implement the not Q output. So it's missing here. So all these ports will be defined in the port list. So we have the clock, the reset signal, the D input, and the Q output. We then declare them that clock, reset, and D are all inputs. The Q is an output. And we also tie this Q. We say Q is going to be a register. So we want to add in this memory element into it, and we call it Q. It's a 1-bit register. If you wanted to have a multi-bit register, you can just use the vector notation that I've shown you on Friday. Just add the limits of your vector. And now that we've done those declarations, this whole thing will be based on a process inside there. When you sort of, in a way, run this module, you don't really run modules, but when this thing is alive, it'll just sit there and do absolutely nothing until something triggers this always block. There are no other concurrent statements, such as assign or any other components that live in this module. There's only this always process. It will sit idle, not do anything, until we either have a positive edge of the clock or a positive edge of reset. Now, let's start with analyzing the reset signal here. This reset will be an asynchronous reset that is assertive high. In order to reset this flip-flop, we will apply a high signal to the reset input, and this will straight away store the value 0 in our flip-flop, and we'll hold it at 0 until our reset goes down. Now the way this thing works, once you are inside the block, whether you were you started running it because we had a tick of the clock or because we had a tick of reset, you check whether the reset signal is asserted. And we said if it's a 1, it will evaluate to true. If it's 0, it evaluate to false. If it is 1, meaning the reset is actually high, then put the value 0 into our register Q. Don't even look at the input D. And it doesn't matter whether we came into this block because of the clock or because of the reset. This tells us that even if we had a positive edge of the clock and reset was still asserted, then don't look at D. Just put the value 0 in there. Otherwise, if reset is not asserted, then take whatever the input is and push it into the register, and therefore it will be pushed into the output because this register is the output. Now, let's go back to the sensitivity list. The reason why I'm triggering on the positive edge of reset and not on any change of reset is because when you deassert your reset, when we go from 1 to 0, we don't want to change the value of the flip-flop. It's only when we are sort of pulling our reset up that we want to, right when we set it up, the flip-flop will be 0, and it will stay 0 while the reset is high. Otherwise, if we didn't have this, then we're just triggering on the positive edge of the clock. Anytime the clock goes high, we will, and assuming reset is low, so this is false, we will put the value D into Q. Here's a question. So this is an asynchronous reset, meaning as soon as we assert the reset signal, this value 0 will be stored in the flip-flop. What do we need to do in order to get a synchronous reset? Meaning the flip-flop will only put the value 0 if reset is asserted and there's a rising edge of the clock. Meaning it doesn't look at the reset signal until the next rising edge of the clock.
Just take positive reset out of the
That's correct. So if we take this whole part here and we only trigger on the positive edge of the clock, leaving everything else intact, is that asserting reset will not actually trigger this block. So we will, as far as the block is concerned, nothing happened around it. But once we go into the block because of a positive edge of the clock, we will check this reset signal. And if it's asserted, then we will store the value 0, giving us a synchronous reset. Here's another question. Could have gotten away with putting a blocking assignment rather than a non-blocking assignment here? Would it make any difference? No, it wouldn't make a difference, and no, don't do it. No difference. Yeah, in this case there will be no difference because there's only one assignment, and after this assignment we sort of go to the end and nothing is dependent on anything that may or may not change. Therefore, you could implement using blocking assignments. It's a good practice when you talk about storage elements to use non-blocking assignments. Now, the idea behind using non-blocking assignments comes when you start having flip-flops feeding into other flip-flops. Whether it's directly like this, similar to a shift register, or through some combination of logic. If you think about it, any of the state machine circuits that we've worked with, in fact, are flip-flops feeding into other flip-flops through some combination of logic. Usually we sort of did a feedback and put the flip-flop one under each other, so it's not that obvious that they are feeding each other, but usually that they are in a state machine. And if you did do blocking assignments into these structures, you might actually assign a new value to the first flip-flop before you then assign the value to the second flip-flop. And therefore, this new value will propagate to all your flip-flops if they were one after the other. Where a true operation of your flip-flops is that each one of your flip-flop that is connected to another flip-flop will take the old value of the flip-flop before we actually change it. And this is inherently a non-blocking assignment. This is why I say use non-blocking assignment for sequential circuits. Yes?
Why do we need the reg queue? Can't we just change the output queue already?
No, because there's nothing that will... First of all, two things. When you have assignments like this, the left-hand side must be a register. If we didn't declare the reg, it will be a wire. You cannot assign values in a process to a wire. That's one thing. And then you can say, well, why not use it as a wire and then use the concurrent assignment outside? Because the concurrent assignment will be continuously processing. As soon as you'll change D, Q will change as well. There will be no storage here. That's all. The case statement, very similar to the switch statement in C. Again, the parallels with C. The idea is to choose one of few different choices and execute only a certain segment of code according to that choice. The syntax will be case and then some expression that will evaluate to a number, and then put the choices of if it's this number, if it's 3, then execute this thing. If it's 5 or 7, execute this. If it's 4, execute this. Default, if it's something else that we haven't had in the choices, then execute their procedural statement there. Now, if you have more than one matching choice in the list of choices, it will choose the first match. If there's no matches and you have the default keyword, you will execute whatever is under the default. If you don't have the default keyword and you don't have a match, you won't do anything. You will just say, no match, I don't know what I'm supposed to do, I'll just continue executing. And I will show you an example in 2 slides' time of how this case is being used. Before I do, the very last keyword that I want to, it's not quite a keyword, well it is slightly a keyword, a parameter. A parameter goes back to the declarations you can put in a module. It doesn't go inside a process, so it's another declaration similar to input, output, register. And if you remember on Friday, we said you use parameters to define constants. Now, there's a few reasons why you might want to use parameters. Essentially, parameters, going back to paralleling it with C, the same thing as either using a const value or a hash-defined value. And we either use it to avoid hard-coding magic numbers into our code. And this is, and this would be a bad programming practice if you just program magic numbers and you have statements like, if x equals 42, then do something. Why 42? Because it's the meaning of life. But you don't know this. So you might, in C, you might do hash define meaning of life 42. And then you say, is equals x, if x equals meaning of life, then do something. You know the context of where it comes. It makes your code a whole lot more readable. So that's the idea behind a parameter here. The other reason why we might use parameters, and again, this is what we might do in C, is to have a quick change of one value throughout our whole program. So we might rely on some value that may change. Instead of then searching for this value throughout the whole program, you use a parameter, use the constant, you change it once at the top of your program, everything else in the program changes, exactly like C. In our context, and this will be in the example I'll show you in the next slide, we will use parameters to give state names, nice English names rather than binary codings, 001, 101, 000, and so on. Remember this guy from week 6? We had fun with him, didn't we? So this is the if you remember the exercise that we had back in week 6, we had when we learned how to build state machines. I said, can we come up with a 1101 sequence recognizer with one serial input, and every time we detect the 1101 pattern, the Z output will go to 1, and then we'll keep trying to detect the sequence. And we've done a few stages, and we came up with this state diagram, and then from this state diagram we use the state table there. Now, I want to take this example and implement it in Verilog. And this is to show you one way of implementing state machines. This is an example of a perfectly good state machine in Verilog. I will give you a couple of minutes to stare through this code, try to understand what's going on. I will start by saying this is by no means the only way to implement this state diagram. This is in fact one of many, many different ways you can go about implementing it. It's one of them, and I do want to go through to see what's going on, the different blocks in this code. The first thing you might notice is that in a way we are describing a bit of a high-level description of this state diagram. There's nowhere does it say what types of flip-flops do I need to use. It doesn't say what combination of logic will actually transition me from one state to the other, obviously because this will depend on the flip-flop type. It doesn't actually specify much in terms of the implementation, but it does specify the behavior of how the state machine should behave. Verilog will then take this description and synthesize a circuit that will do it for you. In a way, you don't care how it's being implemented. You care that it does what you want it to do. There's a few parts to notice here. I will start with the parameter declaration. The parameters are defining my states, A, B, C, and D. Instead of using 0, 0, 0, 1, 1, 0, and 1, 1 throughout the code, now I can say I will use the parameters A, B, C, and D, and therefore I will not have zeros and ones everywhere with no context to them. When you say A, B, C, and D, this will talk about the state. I will have one output Z. I will have one input X, as well as a clock signal, because I do need a clock, and a reset signal that will take my sequence, bless you, sequence recognizer back to its state A, if I'm resetting the machine. I will have two registers of 2 bits each. One of them will be the current state. The other register, and this is just the way I chose to implement this, will be a register that will prepare the next state for the current state. The way I'm going to go about doing this is once I have some current state and some input, I will already calculate the next state in advance, but I will not actually apply it until the rising edge of the clock. In a way, it's like if you have D flip-flops, preparing the D inputs to the flip-flop, so they're sitting there, wanting to be applied, but not actually applied until we have a rising edge of the clock. So that's another way of looking at this. Now, my output, I will define as a register, because I do want to manipulate it inside my processes, my always blocks. And I have 3 different always blocks. Each one of them is parallel to each other. They're all just sitting there waiting for something to happen in the sensitivity list. This always block here will be triggered either when we have a positive edge of the clock or when we have a positive edge of reset. The other two always blocks will be triggered on any change of either X or state. The idea is as such. If we have a positive edge of the clock and we have some next state prepared, as I said, this will apply the next state into my flip-flops unless I'm trying to reset the machine. And this is this check. If I'm resetting, therefore take my state into state A, ignore whatever the next state is. Otherwise, in normal operation, just apply the next state to being my current state. The other two blocks will calculate, one of them, this one, will be in charge of calculating, preparing the next state. This one will be in charge of making sure that we get the right output as we transition. Now both of them, because it's a milling machine, both the next state and the output are dependent on both the current state and the input X. Any change in one of them will then trigger a change in either the next state and in the output. So for example, if my input changes at any time, this will be executed and we'll say, well, what state am I currently in? If I'm in A, do this. If I'm in B, do this, and so on, C and D. Now this thing says, if I'm in state A, for example, then my next state, well, hold on, this will depend on my input X. I might want to go, and this is, if you look up there, if X is 0, I want to go to state A, stay in state A. If X is 1, I want to go to state B, and this is what's happening here. Now, you might say, but they flipped from the table over there, just because you have to realize that if X is true, if X is 1, this will be applied. If X is 0, this will be applied, which is reversed from how I wrote it in the table there. That's the difference. And if you look at this thing, essentially, this is just a table there. So it makes it really easy to just transport from the table into a Verilog code without messing too much with equations and implementation and combinational gates. Similar thing when I'm calculating the output, in a very similar idea, I'm saying if my current state changed or my input X changed, then according to the table there, if I'm in states A, B, or C, Z will always output 0. So I don't actually need to check whether X is 0 or 1, because it's redundant. It's only in the case when I'm in case D, I need to check whether X is 0 or 1, because each one of them will give me a different output. In fact, if I wanted to be slightly more efficient, I could have just got rid of this whole thing and then just say, in the case of D, Z will just follow X because it happens to be the same value. All right. Everybody understand how this whole thing sort of plays with each other? All right. If you're not sure, I'm still going to be here. Come and ask questions.